and thank you for the invitation. I'm very happy to have this opportunity to share some of my recent work with my supervisor, Professor Qiu and Bernhard Keller. The main goal of this talk today is to introduce the construction of DG orbit category, and then realize the perfect derived category in two ways. Let T be a triangulated category and F be a triangulated equivalence on it. The orbit category T quotient by F is the additive category whose objects are the same as the object of T, and the morphisms are given by the following direct sum. Some famous examples of orbit categories are the root category introduced by Peng and Xiao to realize the simple Lie algebra, and the cluster category introduced by Boehm, Marsh, Reineck, Ritten, and Todorov to categorize the cluster algebra. But however, in general, the orbit category are not necessarily triangulated. For example, when the hereditary assumption is removed, the orbit category perfect A quotient by the self-functor composed with some shift is no longer triangulated, but it has a triangulated Hall introduced by Keller in his work in 2005. The triangulated Hall is given by something like the singularity category of B, where B is the DG category. B is the DG algebra, A direct sum with the dual of A shaped by some degree. And moreover, when A is hereditary, this triangulated Hall coincides with the orbit category. So we want to give a canonical way to construct the triangulated orbit category. That is, let T be a triangulated category endowed with a DG enhancement, and F is a DG endofunctor of the DG enhancement. If moreover the induced functor H0F is the equivalence on H0 of A, then the triangulated orbit category is what we want. More precisely, it is the DG orbit category of the DG enhancement, and then we take in the pre-triangulated Hall. And finally, we take H0, and then we get a triangulated category. Here, the DG orbit category A quotient by F is defined to be the DG localization of the left-left quotient with respect to some special morphisms. And due to the limit of time, I will not introduce the details. And in this case, the H0 of the orbit category is something more or less of the Euro orbit category. Next, we introduce some nice property of the pre-triangulated orbit category. The first one is the universal property, which is described by the Z equivalent category. More precisely, the quotient goes from A to the pre-triangulated DG category, induce following isomorphism in the homotopy category of DG categories. And the right-hand side is the Z equivalent category, consisting of the Z equivalent functors from the pair A and F to the pair B and the identity of B. And B is a pre-triangulated DG category. The second one is taking DG orbit quotient commutes with taking DG quotient. That is, we have a short exact sequence of the triangulated Hall among these three guys. This one is the triangulated Hall of the DG orbit category, and the left-hand side and the right-hand side, these are the subcategory and the quotient. Next, we can see examples, that is the bigraded Calabi-Yau algebra. Let A be a smooth, proper, and connective DG algebra. We can take pair XA to be the X Calabi-Yau completion of A as the differential bigraded tensor algebra. Here, HH is a cofibrillant replacement of the DG bimodule, and X minus 1 indicates the shift by degree, minus 1, 1. Here, this symbol X indicates the Adams degree, and this 1 indicates the cohomology degree. And we take EX to be the differential bigraded trivial extension algebra. A direct sum with the dual of A shifted by some Adams degree. And moreover, the bigraded cluster algebra is a perfect derived category quotient by a perfectly valued derived category. And dually, the bigraded singularity category is the PVD quotient by perfect. Here, the superscript means the perfect or PVD of differential bigraded algebra. Our main theorem is that the perfect derived category can be realized in 2 ways. One is as the bigraded cluster category, and second one is realized as a bigraded singularity categories. That is the functor phi and psi. These are triangulated equivalents. And moreover, the upper row and the lower row can be connected by Koszul duality. Finally, we consider an application, that is the n reduction. There are projections pi n collapsing the double degree A and B into one single degree A plus B dot n. And this one induces the functors between corresponding perfect derived category and perfectly valued derived category. That is the upper ones in black. These are the categories we obtained in the last page. And the category in blue, that is the classical result in Amut, Guo, and Keller, who studied the generalized version of higher cluster category. And since that the triangulated category in black all have natural DG enhancement with pi n as the corresponding functor. And under this equivalence, the collapsing functors becomes the set functor composed with some degree. Due to the uniqueness of the triangulated orbit category, we have that the category in blue, and that is the lower ones, are the triangulated orbit category respectively. By combining this with the commutative property we have obtained before, we can obtain this commutative diagram. Yes, that is, we can connect the categories we have obtained in our theorem and the categories in Amut, Guo, and Keller's results. We can connect these to short exact sequence of a triangulated category together. Thank you for your attention.